Hi guys, so I've got this motor here hooked up on it, and I got some caps here laid out for the frequencies. They control the timing circuit frequency. So what I have here is first set that I have in there will be 2.5 kilohertz is what it's gonna oscillate the driver circuit at. I think the second set here is, these ones are around 1.8, I think. What else I have here? These ones are around 760, and these should be some lower ones. I think these ones should be around 350 hertz. And these ones I think are $250. Yeah, 250. I can also get some that'll resonate around 60 hertz too, if I have time. I'm going to start with these here. I have the 2.5 kilohertz. Let me just turn on the yeah, you can see here on the scope it's 2.7 kilohertz. It's just on steadily because the rotor's not turning. It'll start the motor up. I'll let it get up to speed and then I'll take some voltage measurements here. This battery bank here on the bottom is the higher voltage one, and it's at 55.73. I ran it for a bit, so it's a couple points higher than the last few videos. Let's just check what these inputs are. Should be around 13.25 or so. Voltage went up, 13.2827. .28. I've been sitting here, so I'm resting a bit higher. And this other battery here should be a couple volts less than the other one. 53.71. Put it back here. And the same as before, this is the voltage of that one coil right here, and it's got the frequency on it up top there. Once it gets up to speed, I'll take some measurements of the current with the current probe, current clamp. And I'll be measuring the higher voltage battery here, the one on the bottom, right here, because it's the closest to me right here. This is the input for that battery, and that's the output. I'm going to try to do every test with it around 50 milliamps on these gauges, just for easy reference to get them both working together, same current levels. This one's a bit high. Try to keep them with each set of caps at the same current going in on these gauges. They're not very accurate because it's pulsed. I think there's somewhere around 230 130 milliamp pulses going in when I check with the oscilloscope what the real current is. So it's just a hair higher. Right there. Glare in here. If you hear any extra noises, it's really windy outside. So we're pretty close to the, like it'll get up to about 130 or so hertz. But it's pretty close here now. I'm going to start measuring. Then I'm going to put a load on the motor and we're going to measure it, the current. So bring this up so we can see it better. Zero this out. Zeroed out. Down is power coming out of the battery. I have it hooked up, and when I hook it to this wire, it's the opposite, so it's still down. And you'll see the on the bottom on the output, it's still, because it's going into that battery. I've got it reversed here, the way I'm clamping it. So let me just pause this and take some readings here. Going to be pretty generous here with these output readings. Go 22 millivolts. This is set for 1 millivolt for 10 milliamps on the probe here, and this is at 20 millivolt scale here for division here. So we're at 22 millivolts. It means it's 220 milliamps. So it's 13.28. Oops. Times 0.22. 2.9 watts on the input. And I'll go straight to the output here, turn the scope back on. So that's the output now. We're looking about 132 milliamps at 55.73. .3 watts on the output. So now let's just put this back on the input. The motor, you can see it's not going to go up very much more. It's at 136 hertz. Put this back on the input here. And I'm going to just get this down here to where to the lowest is right about there, 236 milliamps right there. Take this off. Now I'm going to put the load on the motor. So the more current going in should come down. We've got a load on the motor now. What you'll notice is this will get wider. It's because the motor is slowing down and it has more further away to the scope is timed. It'll make this wider. It's just taking a snapshot of that. It was so many nanoseconds or milliseconds. These LEDs, this is straight AC current coming into the LED. One LED is facing one way, the other one's facing the opposite way, so they oscillate. They're using both sides of the sine wave, because that is a pure sine wave on that coil. But you see, it's not slowing down very much more. It'll slow down a bit more, but it's pretty close to where it's going to level out. Probably go down to about 7 volts or so. But now let's see where the lowest port is here. So 23.6. I'm going to move this so that line pops up. So it barely moves at all when it comes to that. Very low difference. So now I'm just going to do a quick high-speed run with this, just to see here. The frequency differences. Like every 100 hertz is an extra 1200 RPMs. So like 200 is 2400 RPMs. And 300 is 3600 RPMs. See, it's just pulsed on and off, that's it. See, you're seeing the frequency here, 272 hertz. It's the same as that one. It's because there's no pulsing on here, it's just interacting with the magnets on and off. Full on, full off. So it's 300 hertz, that's 3600 RPMs. it's pulling about 260 milliamps. So now I'm just going to skip right to the lowest caps here I have for the frequency. I've not even tested them, but just for the fact of not having too long of a video here, I'm going to do it like that. I'm going to put this back to where it should be though first. Put a load on this direct short. I like, just to show how much of a drag, like that rotor is probably 3 pounds. It's solid steel and fiberglass with the magnets on it. It weighs a lot. So I'm just going to turn this down and turn this down first though. So when I start it up again, it's not drawing too much. Destroy my gauges. So I take this off. No more power going in. Then I'm going to short it out. And you'll see how fast that coil slows the rotor down because I'm going to dead short it. It's a lot of drag for it to slow that rotor down that fast. It will slow it down to the point where that coil doesn't have enough magnetic field to slow it down anymore. And then it'll just freewheel pretty much. It has to induce enough voltage in that coil for it to affect the rotor. But you can see it stopped it pretty fast. So I'm going to put in these other caps. They're going to be the lowest frequency ones I have out right now. I think they were 250 hertz. Not tried the motor with these yet. Just want to demonstrate the differences the frequency on the pulse width makes. I think they're in there. No, just check. Pulling quite a bit of current. Yeah, I don't want to wreck my gauges, so I'm going to start the motor up and then turn it on. That's what happens when you don't have the cap in the right way. It just turns on. Oh, can't see very good here. Too far away. Should be good now. They're both on. Well, you can see the difference in the frequency here now. So much different. This looks like a big mess. Get up to its normal speed on its own. It's pretty close. Like it'll probably run faster with the lower frequency, the RPMs on the motor, the rotor. Usually that's how it works, but I've not tried these caps yet. Looks like it's going to though. See, it looks way different on the scope. They're running really close to where I want them. So 132 and climbing hertz. So I'm going to turn this back on and start doing some measurements here. I don't think you'll see Overunity with this setup. So this is the input, and you can see how it's consuming a lot more energy like this. You can just tell by looking at it. On these gauges, it's telling me that it's roughly the same as what it was in the last set of coils. Oops. But here you could see the real story, what it's using. Look at how much. So if I just go here, we're touching all these ones. Looking at 389 millivolts for 38.8. So that's what 13.28 times 0.39. 5.17 watts going in. It's going a little bit faster, but not very much. So I'll put this onto the output. Do the same thing here, but go to about there. I'm still seeing Overunity though. .73 times 0.24 and 13 watts. And what was the other one? 13.28 times 0.39. It's actually a little bit better. But the frequency is less, so it's worse actually when you put that into effect. But now let's measure with the rotor under load, because that makes a difference too with the frequency. Here to the last one. this down 40. And I'll put it under load here. Oops. See, this is going to change because of the frequency. You'll notice it more with these lower frequencies. Well, you can see the actual power consumption is going down. Well, it's under load. And you've seen how much of a draw that coil puts on the rotor by just how fast it stopped it. I don't know if you've seen any of my other videos, you've seen what it does to markers and stuff. It just shreds it. So it looks like it's going to level out pretty close to where it's at. Some of the peaks down here, but it's really close to the same. And just adjusting the timing a little bit makes a big difference on that too. You can get it to work even better, but I don't want to touch the timing with this demo because I'm trying to show some different frequencies on the motor circuit and how it affects it. So you can see here on the input what it's at. Let's just check the output again. You can see it's still there. It's actually a little bit higher, it looks like. So now let's just go to another set of caps in the motor here again. Let's go to 500 hertz, 510. Which one's your lowest? If I have them out here. 223. I don't have them here. Okay, let's try 760. Hopefully that's in there. See if those are in there or not. No, I don't think that one's in. Turn it up. Yeah, it's in now. So it's really close to the same consumption here. One thing about this circuit is it runs really smooth. Both sides are balanced really good. When I get more time, I got another big motor to be building. I got too many other things I'm working on right now, though. Once I get more time, that'll be coming. Might even build a big Newman motor too with this circuit. When I get more time, I got another big motor to be building. I got too many other things I'm working on right now, though. Once I get more time, that'll be coming. Might even build a big Newman motor too with this circuit. Show how it's supposed to run. Newman's motors were always pulsed. They weren't just on and off. So that's there now. See, the consumption's pretty high. About there. $312 milliamps. Or 0.14 watts to the output now. There. 208 milliamps. $11.59. I didn't think we were going to get Overunity with that last set of caps at the lower frequency, but it's still not as efficient as these ones are. It all depends on where you want, what you want to do with your motor. If you want to get power out on the, I'm talking, we'll do this. Depends if you want to get your power out from the rotor or into the outputs. What's this down here? $35.6. That's the load. The last tests were showing it. It's pretty. I tested these caps and this setting here. It was actually working pretty good with these outputs when you put the rotor under a load. This frequency works nice. As you can see, this one here is it's went down. There's nothing that's jumping past it anymore. It doesn't have quite as much power on the rotor though, as you can see the meter there, but it's pretty close. Because the consumption on the input is less too, like quite a bit. And you also still have your output working nice. Nice output. Let's just do a high speed run with this, and then I'm gonna end the video because it's getting pretty long. Crank it. See, those frequencies are the same as that now because it's full on. So that's the output, let's check the input. You can see it doesn't really change it even though I've turned it up. It's running pretty much where the pulses are always, you know, to the maximum consumption of amperage. So you're pretty close to the same RPMs too. Just coming up on 3,600 right now. 275 milliamps. Probably get up to like 330 hertz if I just left it run. Another thing I noticed about this circuit is the frequency in the motor is really stable. Where like when you set it, it doesn't move much. See, within 1 or 2 hertz. Performs a lot better than the commutator did. I know that. Because this, like, these motors are just for testing purposes. They're not made for anything else. When I build one that's going to do actual work, this circuit will run it just the same way. But it's a long enough video. Nice stuff. But that's it for this one, guys. Thank you for watching.